The Thevenin's equivalent circuit of this circuit looking out of this base is this circuit, including this 15 volt supply RB1 and RB2. The Thevenin of this circuit is the voltage developing across this RB2, which will be equal to RB2 divided by RB1 plus RB2 into plus 15 volt, which will be equal to 5 volts. And the R Thevenin looking out of this base can be obtained by making this voltage source grounded. Then this RB1 and RB2 will become parallel. So the parallel combination of this will be called RBB, and by using these value we obtain 33.3 kilo ohm. So it is similar to analyze this circuit instead of this. So to analyze this circuit, we have to find the voltage loop equation of this loop and this loop. So if we call this loop as L, so we can write the Kirchoff's equation about this loop L, which will be equal to the VBB, VRB, voltage across this resistance, and then voltage at these two terminals that are present in this loop, base and emitter, so we can name it as VBE, and then the voltage across RE. And by using Ohm's law, we can write IBRB instead of VRB and IERE instead of RE. Notice that the current here within this loop will be the base current, but the current here within this loop will be IE. So it's okay because we already know that the loop current across through a resistance which is common to other loop can have both currents, I1 and I2, that we have done in our intermediate education. So we already know that IC is equal to beta IB and IC is equal to alpha IE. If we know the beta, we can find the alpha parameter. So instead of writing IB, we can write IC by beta, and instead of writing IE, we can write IC by alpha. And we can rearrange this equation for IC at one side and then VBE as a factor of the common multiples of IC and with the VBB. In this equation, we can find IC if we know the value of VBE, because other values we already know. For example, VBB is the Thevenin's voltage we already computed. RB, RE are given, beta given, alpha we can find by using beta. So how to find this VBE? We should remember with the same analysis of diode when we did iterations to find the common point of the free running characteristics of the diode and the diode loop equation of the circuit in which the diode is bounded. So here this transistor, this base to emitter, is bounded in this loop. So its overall behavior, we already know the input characteristics curve, that was the overall behavior. But now this base to emitter is bounded in this loop, so it will try to follow the instructions of this loop as well. So the operating point will be the intersection of this loop equation, which is this one, and the characteristics curve or its equation. We can say graphically curve and computationally it's the equation. So we will do this for understanding in our next lecture. But remember, for amplification, we usually take VBE is equal to 0.7. I will make you understand this as well while we will be discussing the VBE and the loop equation relation. So because we are using it for amplification, and we will be knowing that whoever have designed this circuit, because we are analyzing it, who have been designed this circuit must be considered this VBE at 0.7 or nearby it. So we can take VBE is equal to 0.7. So we already know all other parameters. So we can find IC is equal to 1.38. So what we already know, VBE, IC. So can we find other parameters in this loop, especially the voltages of three terminals of this transistor and the currents? So let's write the Kirchoff's equation about this output loop called L2 here. Similarly, plus 15, then ICRC, then VCE, then RE. Remember, in this loop, two terminals of this transistor is coming. So it can be written as VCE. So it means whatever is the voltage is being divided into these three components. So plus 15 would be equal to ICRC, voltage across this resistance VRC, plus VCE plus VRE. And by using Ohm's law, we can write this VRC and VRE as ICRC and IERE, because we know that within this loop, about this resistance it would be IC, and about this and through this resistance it would be IE. And we already know that IC is equal to alpha IE, so we can write, instead of IE, we can write IC by alpha. And now we already have this IC computed for this whole amplification circuit. We know the RC, we know RE, we know alpha, we know VCC, so we can find VCE. So by putting this value, we have found VCE is equal to 4 volt. And to find VC, to find VE, and or to find VCE alternatively, we can also write this equation, because at VC here the voltage would be 15 volts minus the voltages across this resistance. So VCC minus VRC or VCC minus ICRC would be your VC. So VC is equal to VCC minus ICRC, which again, if we put IC, we know already the RC and VCC, we can find 8.1 volt as VC. And similarly, what would be the VE, the emitter voltage here? It will be the voltage across this resistance, because we are watching it from the ground. So it means VE is equal to IE RE or IC by alpha RE. IC by alpha RE, and if I put IC by alpha instead of IE and then multiply it with the RE, we will find VE is equal to 4.1 volt. And we can find what we desired is collector to emitter voltage about this output loop is VCE is VC minus VE is VCE, which is again 4 volts. So now we have found VCE, IC, the two crucial parameters as far as the Q point is concerned, and also the terminal voltages of VC, VE. And what would be the VB? VB will be equal to VE plus VBE.